I will share with you a quote that I just got from one of my colleagues who is currently teaching Math 102, which is business calculus. So my colleague was teaching shaping rule for derivatives. And one of her students said, "Man, these problems are hard. You can solve these. You should be able to solve all the world's problems." Um, okay. Next, really something when looking at the schedule for a semester of an oddity that I want to address. Okay, here's the schedule. For some reason, okay, so Thanksgiving is November 23rd, and I have here class the Tuesday before, which, considering that this is a late class, that's kind of evil. And then for some reason, no class Tuesday after. I don't know why I have it that way. It was also that way the last time I taught this class in 2021, and I have no recollection of what was going on then. I think none of us knew which end was up. So I'm going to have to correct this so that there will not be class. I'm going to swap these two for November 21st and 28th. So there's not going to be class the Tuesday before Thanksgiving. You know, downtown and maybe some people too. Then there will be class on the 28th. So I'm going to have to make some adjustments, but I'll let you know. Also, you may have seen a whole string of Canvas notifications. Okay. That because the way it's set up before, and again, I don't remember why I had it this way originally. Go back a few years. That the quiz due dates were falling on the same days as the homework due dates, so I shifted the quiz due dates. Again, not that due dates really matter in this class, although, I mean, I'm flexible about these things because, you know, these are challenging assignments and stuff happens and flexible will be good. And unfortunately, that does result in more work being submitted toward the end of the semester. So all of a sudden, it's at the end and like, oh, I have all this to grade. And I've come to terms with that because the end of the semester is hell for all of us anyway. So, okay. But you know, you see how many assignments are. There are some. Okay, I have a rule here in Canvas. Okay, yeah. So homework and quizzes are all lumped together. The whole kit and caboodle is 30% of your overall grade. So the lowest two assignments in this whole collection will get dropped. So I've decided on two to figure, okay, one homework and one quiz, but it could also be, you know, the lowest two homeworks. It depends on what the lowest grades actually are. Okay, now, and we're done with the MATLAB tutorial. So now we shift to a different mode where what I'll be doing is going through these notes. Now, sorry, back to Canvas. So what I will do before class, and you've seen where I have these discussion items for each class meeting. So for instance, for one for today, I will take the notes as I have them before class and I will post them in Canvas just so you have an idea what's coming. But the way, now some of you have seen this kind of thing before. Like if you've had other classes with me that are either online or meeting in this room. So in other words, like, you know, not Cal-free from last semester because I was in a different room. Where I go through these notes, and this is called a WYSIWYG editor. What you see is what you get. Is what that means. So so I'm able to make changes to these notes as I go. And what I will do after class is I will post the updated notes in Canvas. Okay. So we're getting into chapter 2 now. So this class and the next one is where I'll be covering this section 2.1. Now, the notes in here have everything for the entire section, but I'm not going to do all of that today. I'm only going to cover about half the section today. Okay, now, and so far we've really just been dealing with MATLAB, and now it's time to get into the actual subject matter about numerical analysis itself. And I mentioned on the very first day of the semester, numerical analysis is about developing numerical algorithms for solving various mathematical problems. But I've actually seen it written that so the view of some people who work in this field, my peers, that they would think of numerical analysis by definition as a study of errors. It's all about the error in numerical algorithms, and that's, I don't think it captures the whole picture. I mean, it certainly is a essential component of numerical analysis, because we want our algorithms to be accurate. We want them to be reliable, and certainly there are a lot of mathematical software packages out there that use numerical algorithms. People are paying a lot of money for some of those software packages, and they don't want them to be frequently breaking down. Is it raining out? It's raining out. Wow.
Wait, what? It is.
Yeah. I totally did not expect that. And given how hot it was today, that's most welcome. Yeah, that's. Oh, or is that? Who's those damn cleaners?
That's definitely rain.
Okay. Yeah. There's people who like are walking the building. Oh. Okay. Yeah, that's a good excuse. Okay. Well, that's good. Oh, hello, Morgan. Okay. So. Right. Right. But it's not all about accuracy. We want algorithms to be efficient as well. So sometimes you can develop an algorithm that is going to do an accurate approximation, but it could be painfully slow, and we want to see what we can do about that while still preserving accuracy. But for this section, error really is our focus. So in this section, you'll be talking in abstract terms about what an algorithm is doing, because you can always describe an algorithm as an equation of this form: y equals f of x. It's just a matter of what is y, what is x, what is f. So x refers to whatever input you have. Y is whatever output you're seeking. F is the process by which the output is generated from the input. So I'll give you an example. If the problem that we're trying to solve is a system of linear equations, solving x equals b. Then the inputs x consist of all the data that goes into this equation, whatever is given to you. So the matrix A and the right-hand side vector b. The output, y in this case, is what amounts to an unfortunate choice of notation, x. The vector x, that is the solution to this equation. And then then f is process of solving this system. I want to emphasize exactly, like if you were to go ahead and compute x using like whatever process you learned in linear algebra, your row operation, substitution, all that, but being able to carry out all the arithmetic exactly, like using fractions or square roots or however many decimal places you needed. So that would be f. So our goal here is to approximate this process as best we can. So I'm describing the problem in very simple terms, but your input, your output, your algorithm are generally very complicated entities. And what we'll see in numerical algorithms is that there's all kinds of opportunities to introduce error into the process. For example, your input could be erroneous. What if your input comes from measurements? Measurements always have some error in them due to the limitations of instruments. So any error in the input is referred to as data error. What we're more interested in this class especially, is the other kind of error, computational error. So that's error that is incurred while you're trying to compute the output y. So whatever error is caused by your algorithm. Now, to discuss these different sources of error, I'm going to introduce some notation here. So I have like x would be the exact input, x hat is approximate input, y, just plain old y, is your exact solution. That's what we're after. The y hat is the approximation, the approximate output, whereas plain f is the algorithm for solving a problem exactly. F hat is our algorithm for producing an approximate solution. So we're trying to approximate this process, plain y equals plain f or plain x, by this process. Y hat is f hat of x hat. So all of these things, everything in this equation includes some kind of error. So x hat would have the data error. So computational error, right, that's the error in producing the output, but there's different types of computational error that we're going to deal with all semester long. So the first kind is called discretization error. So this is where, because the data that we work with has to be finite. In mathematics, when you're working with things analytically, you're dealing with infinity all the time, like the real number line, for instance. But the number of real numbers you can work with in a computational environment is inherently finite. So you're always going from a continuous realm to discrete realm, and that's going to introduce some error. So for example, if you look at the definition of a derivative, so that's defined as a limit of this difference quotient as h goes to 0. So a discretization of this would be this just taking the same difference quotient, but we're leaving out the limit. We're choosing some small value of h and treating this difference quotient. So that's going to be an approximation of a derivative. And presumably, the smaller h is, the more accurate the approximation will be. Although what we'll find later on is that that's only true up to a point. Another example, evaluating I want to emphasize here, a definite integral. So not an anti-differentiation process, but definite integral. So you're trying to evaluate a definite integral that represents the area under a curve. And we approximate that by a Riemann sum. That also would be an example of discretization error, yes.
Is this gonna be uploaded to Canvas after class is over?
Yes. And any changes I make during class will be included in what I post. I generally have it up like within an hour or so after class. Yeah, so you don't need to worry about trying to take notes like during class. It's all here. Okay. So that's one kind of error, discretization error, that we'll see several examples of throughout the semester. Next, we have truncation error. Some algorithms that we'll see, including towards the end of the semester, are iterative in nature. So you have some process that would produce the exact solution. It could run infinitely many iterations, but of course you can't do that. You have to stop sometime. So that's going to introduce some error. We call that truncation error. An example of this is the file I showed you during the MATLAB tutorial, Newton square root.m, that used Newton's method to compute the square root of 2. And it ran for 5 or 6 iterations. It stopped once the difference in approximations was very small. So there's still going to be some error as a result of stopping, but hopefully not much. Another example of truncation error, if you have functions like e to the x or sine x, computers cannot evaluate these functions exactly in a general case. Computers can they add, subtract, multiply, and divide. Those are the limits of our mathematical capabilities. So for functions like these, what you do to evaluate them is you use a Taylor approximation. And it can't be an infinite Taylor series, of course, it has to be cut off after a certain point. But the knowledge of the Taylor remainder can be helpful in determining how accurate the approximation is and how many terms of a Taylor approximation you need. So really, of all the different types of functions we have, not many can be evaluated fully using the exact expression. Polynomials can, certainly. Also, rational functions, because you're just dividing polynomials. But beyond that, not really. And then finally, a round-off error. As I mentioned a few times, every arithmetic operation is going to incur some error. In the next section, 2.2, we're going to take a very close look at that. But it's a consequence of, again, limitations. And we're all aware of transcendental numbers like e or pi that have infinitely long decimal expansions, but we can't have that here. So those are different types of computational error. Any numerical algorithm we're looking at, we're going to deal with all of these at once, unfortunately. So there's lots of opportunities for things to go wrong. And then actually, the difficulties you can have are not limited to whatever algorithm you're using. Sometimes the problem itself, the underlying problem you're trying to solve, is, for lack of a better word, problematic. We like our problems to be what is called well-posed. Now, well-posed often comes up in a class on partial differential equations, but it really can be applied to mathematical problems in general. So, a well-posed problem is what we should be going for, that it has a solution, and then there's a lot of work done in various fields of proving that a problem has a solution without giving you any idea of how to get it. Love those non-constructive proofs. The solution, preferably, should be unique. And then this next one is most important for numerical algorithms. The solution should depend continuously on the data. And what I mean by that, that's always how this condition is stated. And that's not very intuitive, but informally what that means is, if there's a small change in the input data to a problem, that should not cause a large change in the solution. So like if you're solving a system of linear equations, so ax equals b, and you change b, the right-hand side, by a tiny amount, preferably that should not change x by a large amount, just because b got tweaked a little bit. Unfortunately, that can and does happen. Actually, think it'll come next semester, like if you continue on to the second class, where I can illustrate that for you. So one example, one of my favorite examples, is a concept from linear algebra called the Jordan canonical form of a matrix, which gives all the information about a matrix, its eigenvalues, eigenvectors, and generalized eigenvectors. It is actually not a continuous function of a matrix entries. So it's possible to change the underlying matrix by a little bit, and that could change the Jordan form drastically. And that's not something you want for numerical algorithms. They actually tell you, don't bother computing this numerically for that very reason. You can't trust the answer. So when you have a problem that is ill-posed, especially due to this criterion right here, if a tiny change in the input can cause a large change in the output, how can you trust the solution? Because if the input itself is erroneous, again, because it came from some measurements, then and in fact, if you throw off the solution by so much, then that's going to give you trust issues when it comes to your output. Unfortunately, there are a lot of very important problems that are difficult to work with because for this very reason that the solution can be very sensitive to changes in the data. And we have to keep that in mind when developing numerical algorithms, because you can have a problem that's difficult to work with, and by trying to solve it numerically, you could make the situation even worse. And we need to try to avoid that. But just because the problem is ill-posed doesn't mean you shouldn't touch it. And here's an example that's actually from my research, something I worked on a long time ago. It's called the Perona-Malik equation. It's a partial differential equation that comes up in image processing. And it's a pretty new one. It's actually formulated in 1990. Is technically an ill-posed problem. It does not meet all three of these criteria, but you can try solving it anyway, and it's used to enhance images. So if the input data to the equation is an image, like the pixel values of an image, solving the Perona-Malik equation, the output is an enhanced image where noise or fuzziness is removed, or whatever edges in the image can be sharpened. Okay. But for most part, try to stick with well-posed problem. Okay. Any questions so far about the sources of error and so forth? Okay. Error measurement. So most fundamental concepts in error analysis we have right here. If y is our exact, plain y is our exact solution, y hat is our approximate solution. So the absolute error is just different between them. So approximate minus exact. There's also relative error. It's the absolute error but divided by the exact value as long as y is non-zero. You can think of relative error kind of being like a percentage error. So for instance, if the relative error is 0.01, then you can say that the relative error is 1%. Now, so here we have two competing concepts of error. Which one should we use? Let's take a look. So here's a couple examples. We have exact values y and approximate values y hat. And notice that in both cases, the difference between them is the same. So here y hat differ by 0.1, and also here. So the absolute error in both cases is the same. But if you want to try to judge which one of these approximations is more accurate, it's worthwhile to look at the relative error, because for relative error, we're going to take the absolute value, absolute error, 0.1, and divide by the exact value. So for this first approximation, the relative error is 0.001, so it's nice and small. Whereas for this one, because the exact value, 0.5, is much smaller, the relative error is much larger. So you can say, oh, the error here is 0.1 in an absolute sense, but in a relative sense, you're off by 20%. So it's like, that's not very accurate. So it's reasonable to conclude that this approximation is the more accurate because its relative error is much smaller than the other one. So you're off by only 1/10 of 1%. But this could go the other way. Here's another example of y and y hat, where both values are extremely small. So the exact value is 10 to the minus 8. And then here we have 1.2 times 10 to the minus 8 for the approximation. So because the two values themselves are very small, the absolute error is also going to be very small. It's going to be like 2 times 10 to the minus 9. But if you take the difference between these two that's very small, and then you divide by y, the relative error is going to be large. So given these three contrasting situations, what should you do? So the rule of thumb here is generally you should use a relative error to judge accuracy unless the exact value is, if you don't know anything about the exact value, is close to 0. Another way to describe it is this. You might not have seen this notation. Sometimes it comes up in other classes. When you have a double less than, what this means is much less than 1. Now, much less is not rigorously defined. It's a guideline. So what we're saying here is absolute value of y is very small. So when you have a very small exact, if you believe the exact solution is meant to be very small, absolute error is best in that case. Otherwise, like for instance, if the size of y is greater than 1, I recommend relative error in that case. Now we're going to build on absolute relative error. It's called forward and backward error. So, as I mentioned earlier, we're trying to approximate this process, computing y from x using some algorithm encoded in f. By this, y hat is f hat of x. So same x is going in, but we have an approximate algorithm to produce an approximate solution. So all this is to say, this computational error is the distinction between these two. So forward error is the error in the output. So and you can have absolute or relative forward error. So y hat minus y or y hat minus y divided by y. And I say this is the error that we actually care about because it's what we're trying to produce. And we want that to produce that as accurately as possible. So the goal of error analysis is to get an idea of as to how large this is or how large this is. The trouble is that can be difficult to determine. And what can help us is what's called backward error. So backward error is error in the input. So x hat minus x, or the same thing divided by x. In some cases, this can be easier to quantify, even though it's not really what we're looking for. And as far as how we relate, that's something I'm coming to momentarily. Now, up here, I haven't mentioned x hat at all. What is x hat? And this gets into what is called backward error analysis. So this is how error analysis for numerical methods is often conducted using backward error. The idea is, this is what you're actually computing. So f hat applied to your input x. In backward analysis, what you're doing is you're assuming that your approximate solution is equal to the exact solution of a nearby problem. So in other words, the approximate algorithm applied to the true input is equal to the exact algorithm applied to an erroneous input. And the difference between these two, x hat and x, that's what we call the backward error. And the reason why this is done is if we make this substitution up here in place of this, f hat is no longer playing a role in our error analysis. So we're dealing only with the exact algorithm f. So this is why we do this, to simplify matters. Also, because y hat and y are now both values of f, that lets us use a derivative of f. That's something I actually will be doing shortly. Now, I'm going to show you some examples that are actually from a text of computing backward error for a specific case. So the idea is you're given some input, which I'll call X naught, like a specific number. Here's what you're trying to compute, and then this is your approximation of that. So this would be our forward absolute error. It's just the difference in your approximate value and your exact value. But because of the assumption of backward error analysis, this can be replaced by regular f, evaluated and modified input. So the difference between these two values, that's the backward error. So now I'll show you how we can go about computing these things for a particular example. Okay. Oops. All right. So let's suppose what we're actually trying to compute is sine x, which is something a computer cannot evaluate exactly. And suppose we're trying to compute it at pi/4 radians. Okay. So let's suppose an approximation is this. So it's limited to 4 decimal places. So if I were to look at the forward error, that'd be y hat minus y, which can also be abbreviated as delta y. That's just the difference between these values, which is approximately equal to this. So at least it's reasonably small absolute error. So to get the backward error, what we do is try to find out what input plugged into the actual sine function, in other words, our exact algorithm, or our f, gives you the approximation. So in other words, our x hat in this case could be given by inverse sine of our approximation. So, okay. So then we have our modified input, and we can compare that to the true x of pi/4 to get the backward error. So, and that's what we have here. And so in this case, because sine x is a pretty well-behaved function, it'll be these two outputs. It'll be the exact value and the approximation are close together, and those are equal to the sign of inputs that are also close together. And we see that the forward error and the backward error are about the same order of magnitude. They're both order 10 to the minus 6. But that doesn't always happen. Sometimes it could be of very different magnitudes. It just depends on the function you're working with. This is another one involving the exponential. So we have at x equals 5. So e to the 5 is our exact value. And this is our approximation, again, to 4 decimal places. So we can use that to get our forward error. To get the backward error, we note what we've determined is e to what modified x is equal to our approximation. And we can find it out by taking the log of our approximation in this case, and we get this modified input, x hat. So now we have the backward error. And notice what happens here. The backward error is on the order of 10 to the minus 7. The forward error is on the order of 10 to the minus 5. So both are small, but this is about 100 times larger than the backward error. So the error in the input got amplified significantly in producing the output. So if we contrast these two examples, the sine and then the exponential, Can anyone tell me, based on what you know about these functions, sine x and e to the x, why in this case, the forward and backward error were about the same magnitude, whereas in this case, the forward error was much larger?
Because it's an exponential function.
Yes.
Gross.
Yes, it grows very rapidly.
Yeah.
Oh, it's also worth pointing out, here I chose x equals 5, and yeah, it is growing pretty rapidly there. Whereas if I had chosen a negative value of x, it'd be a different story. But yeah, I'm in this part of the domain, yes, it's growing. If I had chosen a larger value of x, it would have been even worse. Okay. Any questions about forward versus backward error? This comes up in like one of the homework problems coming up for math section. This is actually from homework 2. We're dealing with cosine, and then this is your approximation. So you can plug, the next value into here to get an approximate value. In this case, at x equals pi over 4, so then you would find out at what angle is cosine equal to your approximation, to solving an equation in that case, to get your x hat. So the same idea is what you see in these examples. Now, if forward error is what we really want, but in some cases backward error is easier to get, how does that even help us? And that's where conditioning comes into play. So problems, not algorithms, problems can be well conditioned or ill conditioned. So I want to emphasize the property of a problem, not the method you're using to solve it. Because if you take, for example, solving linear system, A is equal to B, there are many algorithms out there that are very different from one another for solving that kind of problem. Some are more stable than others. But stability is about the choice of the algorithm. But no matter which algorithm you're using for a problem like AX equals B, the problem AX equals B might be badly conditioned, which poses a problem for all of those algorithms. So what is conditioning? Conditioning is quantified by the condition number of a function f. So in other words, our exact algorithm. It's just forward error divided by backward error. It's a ratio over 2. Now forward error and backward error, we've seen for both of these that you can have absolute or relative forward error, backward error, which means you can have a you can have an absolute or relative condition number. Most times we're dealing with a relative condition number. So the idea is this: if you have some idea of how large the backward error can be, and if you're able to estimate what the condition number of your problem is, then you can use this relationship, condition number is forward error or backward error, to estimate the forward error. So that's how error analysis often works. You try to have some quantification of backward error, some quantification of the sensitivity of a problem, the conditioning of it, multiply those two, and you have an estimate of how big a forward error could be. I can estimate a condition number. So here I'm dealing with the absolute condition number. So it's a ratio of the absolute forward error and the absolute backward error. But remember, y is f of x by definition. Now y hat was originally defined to be f hat of x. But remember the assumption of backward error analysis, the approximate solution, approximate value is the exact solution of a nearby problem. So it's equal to the true f and a modified input x hat. But this right here, that's a derivative. So by the mean value theorem, we can approximate this by the derivative at some point. So derivative of your f, your true algorithm, in magnitude, is the absolute condition number. And I don't have the relative condition number written here, but I do have it here in the text. Okay, so if I do the same process for relative condition number, so relative condition number is relative forward error divided by relative backward error. So delta y over y or delta x over x. Then I rework that fraction down here, and then I fill in what the definition of delta y is. And again, a derivative appears. So this is our estimate of the relative condition number using the derivative. So xf prime over f. All right, so here's an example involving forward error, backward error, plus the condition number. So our true function, we'll just use x cubed. And our true input is x equals 4. And suppose we have some knowledge based on the context of our application that the input can be off by at most 0.1. So x hat can be like between 3.9 and 4.1. So we want to use a condition number of this function to estimate the forward error, both absolute and relative. Start this on a new page so we can see it all at once. All right. Now, okay, so since this difference is at most 0.1, that is the absolute backward error. And then I divide this by our true x4 to get to relative backward errors. Now we have both backward errors. Now, here we have the approximations of our absolute condition number and our relative condition number. And since we're doing a very simple function here, x cubed, can go ahead and fill in all of this. So here we have a derivative, and we evaluate it at our true x value, so x equals 4. So the absolute condition number of x cubed turns out to be this at x equals 4, so we get 48. The relative condition number turns out to be just 3. And so it turns out, if you look at what's done algebraically here, the absolute condition number depends on x. So if x increases, it's going to grow. Whereas the relative condition number, it always works out to be 3, no matter what x is. So then, I take my backward error times my condition number, and I have my estimate of the forward error. So here I have it for the absolute case, 4.8. Then for relative error, 0.075. So this is illustrates the process of having the backward error analysis. Is backward error times the condition number, which comes from your true function. We're not talking about any approximation of x cubed because it's independent of that. So what I can do is I can check these estimates. What if I chose an x hat that was within range? So x is 4, so I choose x hat to be 4.1. Then I go ahead and plug that into x cubed, I get this. So then I can get absolute error and also relative error with these like erroneous inputs. And notice that the absolute error, 4.9 compared to 4.8, then we have relative forward error, 0.0769 compared to 0.075. So actually these estimates were quite good at quantifying how much a change in the input causes a change in the output. Because it's taking into account the nature of your function f and how error could be amplified or not. Also, here we have this pretty small backward error in the absolute sense. the absolute forward error is much larger, so the error gets amplified in absolute sense. But and only amplified some in the relative sense, but not as much. So any questions about how forward error is estimated? So later in the class, when we study specific problems like polynomial interpolation or numerical differentiation, numerical integration, or solving a nonlinear equation. So those are the fundamental problems we'll be considering all semester long. These concepts of error analysis will be applied in those settings. Okay. Now, as I mentioned, conditioning is a property of the underlying problem you're trying to solve, whereas stability is a property of the algorithm that you're using to solve it. I want to discuss that. Let me distinguish the two. So let's suppose we're solving system linear equations, and we're using Gaussian elimination, like we learned to do in like Math 326. And let's suppose the matrix is well conditioned, but will also, so in other words, a change in A or B will not lead to a large change in X. So it's a well-behaved problem. But also suppose that the 1, 1 entry of this matrix is an extremely small number, 10 to the minus 10. Now, because this element, though small, is still non-zero, you can go ahead and carry out your row operations, and it's not absolutely necessary to interchange the first row with another row. That's called Gaussian elimination without pivoting. Pivoting refers to row interchanges. So what we'll learn, this is actually a topic for next semester, but we're learning about algorithms for solving X equals B. When it's a computer doing the work, it's not necessary to interchange a row in this case, but it's a very good idea to do so. But by not interchanging rows, not doing that in this case, that would be a numerically unstable algorithm. Whereas if I do perform a row interchange, it's actually been proven that this kind of approach, like whenever you have a small value like this, and if you do interchange rows, there's actually proven that that is a numerically stable process. This is actually a serious issue back when electronic computers were first invented. So a long time ago, like in the, I guess the late 40s or 50s, when Gaussian elimination had been in existence for a very long time, actually literally thousands of years, just not named after Gauss, because Gauss had nothing to do with the invention of Gaussian elimination. I know I'd love to have my name accidentally attached to an algorithm, but so private name will do it on purpose. But you know, before it had to be carried out by hand. Once we had electronic computers, and the issues of computer arithmetic, as I said, every operation introduces some error. There was concern that carrying out this Gaussian elimination process would simply be numerically unstable and therefore couldn't be used. And that would have been terrible. What do you do? But it was proven that if carried out carefully, it actually is numerically stable. So I think the numerical analysis community breathed a big sigh of relief over that one. So the importance of both conditioning and stability is that if your problem is well conditioned and you have a stable algorithm for solving it, then you can expect that the approximate answer that it produces is an accurate one. Unfortunately, for a lot of applications, we're not likely to have both of these be true. Like pretty much all the problems I deal with in my research program are terribly ill-conditioned. Okay. That's actually as far as I want to go in this section today. There's still more material, but that's earmarked for Tuesday. So we have this time for any questions either about these fundamentals of error analysis or about any homework questions, like MATLAB. I sense people backing up, which you're also welcome to do. So open to y'all.
Exploration 1.2.5.
Okay. Okay, so, so if you use the RAND function, like it's done right here, that will give you random numbers that are distributed within the interval of 0 to 1. So in this case, the goal is to come up with a matrix, a 3x2 matrix, where the numbers are distributed between -1 and 1, and uniformly distributed in that interval. So what this boils down to is, how do you it amounts to shifting and scaling, a linear transformation of the interval 0 to 1 to the interval -1 to 1. So, okay, because you can map any interval, AB, to any other interval, CD, by taking values from AB and shifting and scaling them. So, and now in this problem, we're only going to focus on this one case, transforming the interval from 0 to 1 into the interval from -1 to 1. So, I'm going to type this into the notes. Okay. Put it right here. So the idea is, how to function a linear function that maps the interval 0 to 1 to the interval -1 to 1. And you apply that transformation, the linear transformation, to the matrix that you would normally get from RAND that has numbers 0 to 1. So, what I mean by that is, how do you shift and scale the interval 0 to 1 to obtain -1 to 1? So these are the two operations that would need to be performed. So I'll give you an example other than this one. Okay. So to map the interval 0 to 1 to the interval, let's say 0 to 4, you'd use f of x equals 4x. That would, in this case, only scaling is necessary to map from this interval to this one. For another example, to map, say, interval 0 to 1 to, say, 2 to 3, x equals x plus 2. So this would involve, so this first example is only scaling. This one is only shifting. To map 0 to 1 to -1 to 1, you have to do some combination of both of these operations. So in this case, if I compute this matrix R equals RAND, And if I were to multiply this by 4, I'd have uniformly distributed random numbers from 0 to 4. If I were to take this matrix R and add 2 to it, then that would shift random numbers to be between 2 and 3. So see if you can use these ideas to go of a similar function that would map this interval to this one. Give that a try. Summarize what I was saying. Others?
Scaling and shifting.
So here we have an example of scaling, here we have an example of shifting. But doing only one of these operations is not possible to go from 0 to 1 to -1 to 1. We need to use both operations in combination. So one way to think of it is like if you choose one of these as a intermediate step, and then it won't give you -1 to 1, but then how can you do the other operation to fix it? Because you take into account that this interval -1 to 1. Hang on. Yes, I'm going to grumble about this editor all semester long, deal with it. Get used to it. -1 is an interval of length 2 with center on a 0. So scaling changes the width of the interval, while shifting changes the center. Now, for 0, 1, the width is 1, and the center is 1/2. So neither the width nor center are what you want. But because okay. Try all of this in writing. 0. Whereas interval 0 to 1 has width 1 with 1 center 1/2. So that's why you need to use both operations to change 0 to 1 to -1 to 1, because you want this width and center, but you have currently this width and center. They both have to be changed. You can talk about it in your group or something. One of my colleagues actually wanted to ban that. You pursuing group this college? But
Why, what'd you say?
one of my colleagues, very good friends, wanted to ban use of group on campus or something. And then was told it was not technically feasible.
Ban the use of GroupMe.
Yeah, I guess there's been situations of like students using GroupMe to like stir up the other students in the class and revolt against the professor or something like that. I think your professor was experienced that and you started examining what you're doing. I mean, that takes motivation to do all that. Okay. Other questions about? Or if you're just over it, you can just go. I mean, since class time is not over yet, I'll certainly say, for anyone stuff. I guess we for the class is complete. Section on